Good morning to you all. Thank you for the invitation to talk to you about adsorption, desorption of three organic semi-volatiles on Arizona test dust and kaolinite clay. First, I would like to thank my co-workers, Riccardo Iannarelli, Horst Pick, and Christian Ludwig for their valuable input and discussions. I would like to structure the presentation into several parts. First, I will talk about the measurement technique, which includes a flowing gas experiment. Then I would briefly talk about the semi-volatiles and mineral dust interactions from a chemical kinetics point of view. Then I would like to talk about some desorption experiments that give insight into the lifetime of adsorption of these organics on mineral dust materials. And then I would like to open and close a bracket because I would like to compare the behavior of the probe gases that we use to explore the physical-chemical characteristics of the surface. With amorphous carbon, because there's a lesson to be learned. And then I would like to come back to the mineral dust materials proper in order to discuss the chemical makeup or the composition of the interface in terms of surface functional groups. And then it will be topped by a conclusion. As one slide of introduction, I would just like to say that the desert region in the world actually comprise 1/3 of the global landmass. Of these desertic areas, about 1/3 already are cold desert like ice and tundra, and 2/3 are hot deserts like sand and arid or semi-arid areas. And you can see rank number 1 and 2 are cold deserts. They are the most important ones. Are the Antarctic and the Arctic desert, whereas all the other ones are distributed, I wouldn't say evenly, but over the globe. The important thing is, for comparison purposes, the budget for the input here on the lower right into the atmosphere is between 1 and 6 gigatons atmospheric dust per year. With only a fraction, about a few percent of it in terms of volcanic dust. However, the latter may reach up to 10 gigatons per year in a good volcanic year. So we can in no way just ignore the input of volcanic dust. For instance, in 1991, Mount Pinatubo in the Philippines, Mount St. Helens in 1980 are examples of large volcanic eruptions that discharged a lot of volcanic dust or volcanic ash into the atmosphere. For comparison purposes, the global CO2 emission in 2020 was 31 gigatons per year. So you can see the budget for the mineral dust input into the atmosphere is not as important as that for CO2 in terms of mass, but it is about 30%. And mineral dust by suspension and the action of wind and aeolian activity is the largest source of, or the largest representative of atmospheric particles on a global basis. So let's go back to, or let's come to to explanations or remarks of the experiments that we use. We use a flowing gas experiment, the Knudsen flow reactor, in terms of method to discover the chemical kinetics, the rate of adsorption, the rate of desorption of these organic or inorganic probe gases that we use. It is useful to compare the Knudsen flow reactor technique with the most commonly used flowing gas experiment, which is the laminar flow tube experiment, either in its fast version using helium as a carrier gas, or let's say using the slow variant at atmospheric pressure for suspending atmospherically relevant aerosols. Now, in our technique, the pressure, you have to view the Knudsen reactor as a box, and the box where the flow of gas into the box actually is facilitated by a variable exit orifice that controls the gas residence time. The larger the exit origin, the exit orifice, excuse me, is, the more likely is that the gas escapes, and therefore the static pressure inside is lower than if you work with a smaller exit orifice. So the important thing is that we use gas flows that are enabling experiments at very low pressures. The molecular flow regime is particularly attractive because it leads to very easy interpretation of the results. So we have, owing to the low pressures on the order of millitorr. A millitorr is 1/1000th of a millibar, so a microbar, so to speak. We have no gas-gas collisions, in contrast to the laminar fast flow or the laminar flow tube, which has practically no gas wall collisions. So it's only gas-gas collisions, whereas we have only gas wall collisions. Molecules do not encounter fellow gas molecules in the gas phase, but they collide hundreds or thousands of times more frequently with the walls. And therefore, in order to explore heterogeneous kinetics, namely gas wall or gas surface, gas condensed phase interactions, it is the method of choice to rapidly characterize the chemical kinetics of these heterogeneous processes. The Knudsen flow conditions are realized, or let's say they are given if the mean free path of the gas is about lambda is about 3 times or more the diameter of the escape orifice, meaning that there should be no collisions while the no gas phase collisions between molecules as the gas tries to escape. So this is the slide for the principles of the experimental technique that we use. The pictorial representation of the whole apparatus is given in this slide. You can see this is the proper Knudsen flow reactor, which I will present in the next slide. But the general setup is the follows. The Knudsen flow reactor is fed by the gases coming from a gas inlet line, described here on the right, and in principle goes across an opening into a chamber, which is separated by another chamber housing a mass spectrometer for recording purposes. A molecular beam is formed at the exit orifice of the Knudsen flow reactor, and is chopped by a chopping wheel here in order to modulate the molecular beam. And we call this molecular beam sampled modulated mass spectrometry. The mass spectrometer is a high quality quadrupole mass filter that we park on a certain feature of the mass spectrum, that is the fingerprint of the molecule whose interaction with this solid sample sitting here we want to explore. So the important thing to remember here is that we measure loss rates and not concentrations. We can calculate the concentrations at all times because we measure the flow rate. We know how many molecules come in and how many molecules flow out if there is no interaction, because the plunger actually here is closed. The sample is not in contact or exposed to the gas. It is important to know that we have 2 degrees of freedom to work or choose the parameters of the flow reactor. First, we have well, first let me talk about the setup of the reactor. The reactor is a 2-chamber reactor. So the sample sits here in this separate chamber, lower sample chamber that is closed by a lid. By actuating the plunger up and down, we can open and close or expose or not the mineral dust material that is sitting here in the sample chamber. With the sample chamber closed, we have the simple mass balance that every molecule that comes in, or the flow rate of molecule that is coming in, is the same as the flow rate of the molecules that leave the surface here in the form of a molecular beam. We have on this side a degree of freedom that we can in situ change the exit aperture diameter. We have formally 1, 4, 8, and 14 millimeter apertures at our disposal. 14 millimeter aperture is the aperture that pumps the fastest, that it has the fastest pumping rate, because as I said before, the probability of a molecule leaving a large aperture is much larger compared to the 1 millimeter aperture. 1 millimeter aperture, the smallest one used in this in the present apparatus, is used for building up static pressures that are high in order to probe the adsorption properties of the probe gases that we use with the fixed materials. So we have here, in essence, open and close, and here four exit apertures to choose from, which gives us, in principle, 8 equations of state for the experiments. So what we have here in summary is we observe we measure the net adsorption and desorption kinetics as a function of gas residence time. The experiment will give us the total number of molecules adsorbed in the uptake phase of an experiment, when we start with a clean material, mineral dust material or other material, solid material or liquid, and the desorption yield at a given time. And then we can observe both the reactants and the reaction products, both net kinetics and the number of molecules as a function of time. So that's what we can do on the experimental side. I would not like to dwell a lot on this slide. This slide is actually giving you the BET surface area for the kaolinite and Arizona test dust and Saharan dust. I would like to concentrate in the following part on kaolinite and Arizona test dust in its interaction with the organic species that I will talk in the next slide. So kaolinite has an BET surface of between 22.5 and 15.3 square meters per gram, whereas the Arizona test dust, medium and coarse, has almost the same. Between medium and coarse is almost the same. It's 10.5 versus 10.8 square meters per gram. Saharan dust is a very fine dust, an aeolian deposit from the Sahara that is deposited on the Cape Verdes Islands. That is a group of islands that are actually downwind from the Saharan storms in the spring. Now, for the organic substrates that I would like to talk about today is menthol, which is an alcohol here. It has an OH group. Aplinate, which is an ester, 2 oxygen atoms here, and the pipol acetate, which is also which has 2 oxygen atoms plus an unsaturated, the double bond, a site of unsaturation. And when we measure in later stages of the talk, when I will talk about the desorption, the desorption rate constants that we measured, it is important to realize that the inverse is the desorption lifetime of adsorbed or a condensed molecule that gives valuable information about the kinetics of the desorption and the possibility of further reactions while the molecule is adsorbed. So my talk will be on solid substrates, kaolinite, low ordered or high ordered Arizona test dust, and I would like to exclude our studies at the moment on quartz sand because they are not very interesting because our sample had a very low BET surface area. I would like to remind you that the rate constants of adsorption and desorption that we measure are actually made relevant by normalizing them to the BET surface. So we get a rate constant, either a rate constant or a coverage per square centimeter. So that's it. I forgot to mention that before. So let's go to some examples. You can see that on the left panel here, the blue curve is the mass spectrometric signal of aplinate, which is the ester that you saw on the previous slide, as a function of time. The time is in points, so there are 4 points to the second with an acquisition rate of 4 Hertz. So at this point, we flow in a flow of aplinate. This is the signal, the mass spectrometric signal, owing to the detection of the thermal molecular beam. And it is on the order of, you can see here, 3.1 times 10 to the 15 molecules per second. This is an absolute number. We know what the concentration is. And so at this point, we open the sample compartment, and you can see that you lose, in principle, practically all the molecules in the first moment. And then as time goes on, the signal recovers due to partial and then finally to total saturation of the surface, in this case on kaolinite low order. At this point, we close the sample compartment, and then if there's no other change, then we regard the sample as being totally saturated. At this, then further on, between 15 and 25,000 points, at this or at 23,000, we stop the flow and then wait until no more signal actually is apparent on the screen on the mass spectrometer. At this point, we open the sample compartment again at the exit orifice of 1 millimeter. And then the signal, actually, the applinate is being pumped out from the sample that was sitting in, although that is sitting in the sample compartment. And then in situ, we change to the 4 millimeter. And the 4 millimeter, actually, because of a higher pumping rate, desorb or affords the desorption of more strongly bound molecules. And you can see that if we follow this with the 8 millimeter and the 14 millimeter aperture, you can see that less and less molecules come, because most of the molecules that will desorb at room temperature have already been desorbed. And so we sum these areas up and count the number of molecules and compare them with the molecules that we have lost in total, which is corresponds to the area between the red line and the actually observed signal. I would like to turn to, we will discuss the results in a moment. And I would like to discuss another organic, and this is menthol. Menthol has has a terpene or terpenoid scaffold and has one hydroxy group, which corresponds to an alcohol. And so the challenge here was to look at an organic with a very small vapor pressure. Usually the vapor pressures are between a few torr and, let's say, 10, 15 torr. Here it's 78 millitorr, or 0.104 millibar at the room temperature, 26 centigrade. And so it leads to a very small signal. Remember, here before we had 2 or 3 volts, we have 0.2 volts, and so it takes a while to stabilize the signal. But however, at this point, we open the sample compartment, expose it to the 1 millimeter orifice, to the flow in the 1 millimeter orifice reactor. And then at this point, we see a loss and a recovery. Here we close the sample compartment, and then we see a little change. So this was very close to saturation. Then we do it again. This is the mass spectrum of menthol. You can see it's a very rich mass spectrum, in contrast to small polar molecules that we have also examined. And so you have the choice. Sitting, you get the same results here by opening and closing the reactor, or studying the loss owing to uptake, if you sit on any one of those. The desorption of menthol, of course, is given here in the lower left panel. You can see that once the molecules are actually pumped out at closed sample compartment, we open the sample compartment, and then actually we see residual coming off. These are the molecules that are spontaneously desorbing. We change to 4, 8, and 14 molecules and sum up the number of molecules and put them into perspective with respect to the original loss. Here we do it on kaolinite, and we do the same experiment on Arizona test dust. And here you can see it's the same, it's practically the same scale here, 20 millivolts or so. And you can see that the desorption trace is actually much lower So that means there are much less molecules coming off at room temperature. They're held back by the Arizona test dust, much tighter than the kaolinite. And so that gives you a first impression that the same molecule, the same organic molecule, namely menthol, on kaolinite is bound is bound to a lower degree with a lower energy of absorption than on Arizona test dust. The experiments actually are displayed here in the this table. We have a matrix of 6 times 2 or 3 times 2, 6 cases, aplenate on ATD, on Arizona test dust and kaolinite, people, acetate, and menthol. This is also an ester, so aplenate ester, people ester, and menthol. I would look at the numbers here. For aplenate, we have 25.3% of a monolayer after conversion into the into a relative measure of number of molecules per square centimeter. The aplenate can be adsorbed to a much higher degree on Arizona test dust than on kaolinite. On kaolinite, we have roughly 10% of a monolayer to saturation. Once you saturate, you don't absorb any other molecule, even though the coverage is only 10% of a monolayer. People is 100%, it's 120%, but it's plus minus 20%. You can in terms of a monolayer. So with people, with this ester, you can actually reach monolayer saturation coverage. With the same organic on kaolinite actually leads only to 49%, to about half. Then the prompt desorption, that gives you an important clue, as briefly discussed before. For aplenate, you get 10%, and for on ATD, on kaolinite, you get 60%. So ATD holds back the organic much tighter, and you can see that the trend is also true for the other, qualitatively speaking, also for the other two. Here, 13.4% on ATD is less than 24.6%, and for menthol you have the same, only 3.4% desorbing from ATD, and 27% of kaolinite. Now, I would like to tease you a little bit more with the data, because we would like, even though we cannot observe it in real time, we performed the experiments that after the spontaneous desorption, we let it pump. We changed we let it pump the sample overnight at 14, at the fastest pumping rate we have, namely at 14 millimeter aperture. And then we subjected the sample to the same sample to a second round of aplenate. And at the next morning, or the next day, we could see that it adsorbed 33%, whereas aplenate on kaolinite actually adsorbed 91%. So you can see that even overnight pumping, even though we couldn't observe it in real time, the readsorption experiment gave the same conclusion, namely that only 33% on ATD course could be adsorbed the next morning, whereas whereas for kaolinite, we could adsorb 91%, implying that overnight pumping actually led to much larger loss from kaolinite than from ATD. And so this column here gives you the rate of adsorption of the corresponding organic from the sample. And you can see the same thing is true here for as a function of the type of Arizona of the solid sample of the mineral dust material. Here, 23% could be pumped overnight in 15 hours, roughly. Whereas here, it was 31%. Which means that kaolinite, the adsorption strength was much larger in kaolin on ATD cores than on kaolinite. The same trend here. ATD cores being a much better adsorber for menthol than kaolinite. Okay, I would like to point out that we put the experimental results into formalism, which is the Langmuir adsorption model. And just look at the first, in the interest of time, I would just like to concentrate on the first line. A is a gas molecule, SS is a surface site. So A plus SS in equilibrium, adsorption, desorption to a surface bound molecule A. And so the important thing here is to realize that the rate of adsorption is dependent both on the gas phase concentration of A and the number of free unoccupied surface sites. That's the essence of the Langmuir adsorption model. I would like to symbolically represent the kinetics in terms of this box. This box represents symbolically the reactor, the Knudsen flow reactor, and the arrows here, Ka determines the adsorption coefficient, and Kd, or the absorption rate constant, excuse me, and Kd, the desorption rate constant. Because for the moment, we have information on Ka, and Kd is a little bit more complicated to measure, and all this is dominated or is under the conditions of the rate constant of effusion. So we have a 3-parameter fit to our problem of the governing equation, which is a differential equation that when integrated in analytical form gives you this expression here. Now, I don't want to bother you with this, except that I'm very proud of it, that we found in closed form, which facilitates the analysis, and especially, first and foremost, which enables you to understand the chemical kinetic system in terms of the 3 equations. I don't want to bother you with the numbers that we got, except to say that when you have these logarithmic displays of the experimental data for desorption, 1 millimeter, 4, 8, and 14 millimeter, these are not straight lines. In no way. For instance, this one, and even this one is not a straight line. Straight line would be straightforward first order desorption, because we here plotted it as a function of the logarithm of the experimental signal. So caveat is that the desorption rate constant cannot be fitted merely by a straight line fitting, because it's more complicated. The reason is that during the residence time given by Ke, you not only have the desorption, but you have readsorption. And therefore, it is a more complex expression. This is true. This is not always realized by people in the business, that you have to, when the residence time is finite, that you have to contend with readsorption. However, we did this fitting, and the fitting of menthol to a 1 millimeter reactor orifice on kaolinite looks like this. And you can see here the experiments are in blue and the fits are in red. We have only the situation of a very good fit. Here, the data, as I have shown for menthol on Arizona test dust, there's very little signal, but the initial phases are reasonably a good fit. You can see here the same thing. We know K-escape because we have chosen a certain orifice, and we have measured the rate constants for adsorption. And so in principle, it should be a simple thing to find out what K desorption is. And because the fits are pretty good, this is applinate on the two materials, namely kaolinite and Arizona test dust. In my view, very good fits. And here it's people acetate. Here again, very good fits to the experimental data. Now, in principle, let's look here briefly at the quantitative results. We have measured here you can see Arizona test dust and kaolinite, the results. K0 is the measured value of the rate constants for adsorption, giving rise to the uptake coefficient, for instance. And you can see here, these two numbers are the same that we have used for the fitting. So we really have used the measured value in the fit and have discovered KD using the fitting procedure by adjusting just one rate constant, namely that for desorption. And it leads, the inverse of it leads to the residence time, which is, in this case, Arizona test dust with menthol. You can see that this residence time is fairly long. It's 9 hours. For Arizona test dust, and for kaolinite is about between 25 and 30% that for Arizona test dust. So there's a considerable variability for the same organic molecule in changing from Arizona test dust to kaolinite. Same thing here for applinate. Applinate surface residence time is 4 hours versus 3 hours for kaolinite, and Arizona test dust and kaolinite residence times for people acetate is 0.4 hours and 1 hour. So you can see that the absolute value of the residence times, of the surface residence times of the adsorbed organic on a specific mineral dust material actually varies a great deal. Varies from from a fraction of an hour to about 10 hours for the 6 cases we have examined. That is, the red numbers here are the Lamieux constants. I don't want to talk to you about the Lamieux constants, except to say that these are not they're constants that are characteristic of the gas phase solid pair. And this is a true equilibrium constant in terms of with the units of volume. The dimension is cc or liter, depending on what you choose. So these are the red numbers. These equilibrium constants will become important when you do temperature-dependent studies, because that will lead directly through a Van 't Hoff analysis to the delta H for adsorption and the delta S for desorption, the entropy and the enthalpy of adsorption for the equilibrium system. But for the moment, I was concentrating on the surface residence times of the adsorbed molecule. Okay, let's digress briefly to amorphous carbon that we have examined. It's a processed amorphous carbon, so it's a carbonaceous material that has been processed from an oil, from residuals from cracking and distilling crude oil. And so we have chosen 3 cases, namely in this example here. We have used 10 probe gases. So it's NO2, ozone, trimethylamine, a base, which is sensitive, which will react with surface acidities. HCl is a weaker acid than TFA. TFA is an acid. TMA is a base. So the TMA base actually will look out for acidic surface groups. HCl is an acid and will look out for basic surface functional groups. And we have looked at the trifluoroacetic acid, which is a stronger acid than HCl in the gas phase. Hydroxylamine, which is ammonia, where we have replaced 1 hydrogen with an OH group. And we will talk about this at length later on. SO2, H2S, H2O, and thiophene. And let me quickly point out the situation for NO2, HCl, and water interacting with the amorphous carbon. Here you have this is a trifluoroacetic acid monitored at mass 69. We monitor the loss. You lose practically, like in the case of organics, almost all of it at the beginning until recovery. Here, the specialty is that it leads to a steady state uptake. So we take only the losses that between the red line and the blue experiment. What we have is we have an desorption trace for water, we have an desorption trace for HCl and for NO2, and we would like to fit this again with our 3-parameter model. Now we get good fits. These are reasonably good fits. However, in order to obtain these good fits for water, we had to change the adsorption rate constant by a factor between 70 and 125. If we use the same adsorption rate constants as the one that we measured when the system was dry, namely at the beginning, of course, then we would get an adsorption or a desorption trace that it looks like this, and this is the measured desorption trace. So you can see that we had to do something. We could obtain this fit only by increasing the rate of adsorption of water by a factor of 70 to 125. Whereas for trifluoroacetic acid and for trimethylamine on the same carbon, there's no problem. When we get good fits when the observed adsorption rate constant is equal to the when we use the adsorption rate constant that we observe in the uptake phase, transfer it to the desorption phase. So this is the normal case, and this is the abnormal case. When you coin these results in terms of collision cross sections, then you can see that the increase in the rate constant here is K0 from the adsorption adsorption phase compared to the fitted rate constant in order to get a good fit, qualitatively a good fit. And you can see that we have to increase the rate constant by a factor of 70 to 125 to get a good fit. And that actually is equivalent to increasing the hard sphere collision cross section by a factor of 10 again. You know, it's almost a factor of 10, not quite. To 32 square angstroms, and here 42.5 square angstroms, which is it's the same physical picture. It's a larger hard sphere cross section. The reason for that, of course, will be apparent when I tell you that the two situations are not the same, because in the adsorption phase we have a dry sample, whereas in the desorption phase, where Ka actually is used for fitting in order to see what the desorption rate constant is. At the desorption, the state of the surface at desorption is different, of course. You can see in the beginning, in the dry situation, we have a few adsorption sites for water. Water is not a very good material to adsorb on the hydrophobic surface of carbon. And so you have only a few adsorption sites. The adsorption rate constant is fairly slow. It's on the order, the uptake rate, the uptake coefficient is on the order of 10 to the minus 3 or 10 to the minus 4, in that range. So it's quite low for water vapor. You know, once the exposure to water vapor is done, at this point here, we measure the desorption rate constant under conditions where the adsorption, of course, is much larger, because you have already large clusters present on the surface. And so the uptake is a dry situation, whereas the desorption traces whose rate constants we measure correspond to this case, where the molecules actually have saturated the few adsorption spaces that are available. And so in principle, you do not form films at saturation or when the adsorption actually goes on, but you form either droplets or crystals localized few and far apart, but leading nevertheless to an increase in rate constants, because the cross section of these of this situation is much larger than if you have a small adsorption site for water at the beginning of the adsorption phase. I would just briefly tease you with contrails. Combustion engines actually release not only gas phase molecules, but they release also soot, which is a type of amorphous carbon. And in the modeling world, it was always a big question why the contrails are formed so readily after the emission of the it was the beginning of the contrail actually is about 10 meters or 20 meters right after emission. If you would use the rate constants for adsorption for the dry case, you would see the onset of contrail formation much later or not at all. And so the reason that the contrails are formed so efficiently is because once you have adsorbed a few water molecules, the rate of adsorption of further water molecules is autocatalyzed, is much larger. So the molecules a few molecules that are adsorbed right at the beginning actually attract more molecules to rapidly grow to absorb water and then be converted to ice crystals. So that's an autocatalytic effect that actually explains the rate the efficient, fast and efficient formation of contrails, which is a problem in atmospheric chemistry and the role of aviation. I don't want to go into further details. Just to show you a few years before, there was in 2004, well, already quite a few years passed, we observed droplet formation on soot particles rather than see, this is an environmental SEM picture. It's a macroscopic still, this is 20 microns, but we have a Pyrex surface and a soot surface here, and you can see that and this is not even, this is just water because it's 277 K, and this it's a small onset of a small water droplet, and here some while later it has grown, but nothing else. Here the same thing, we have a soot surface, a crack in the soot surface, and you can see that the droplet, the onset for droplet formation at the coldest point on the soot, but not on the aluminum surface. So the upshot or the conclusion in a nutshell is that we have observed a non-adherence, a non-validity of the Lamieux adsorption model. Let me see here. In the interest of time, I will quickly go through the rest of my presentation. We have the role of relative humidity in adsorption and desorption phenomena is complex. Sometimes, like in example A and C, you can see that the uptake coefficient of water, here is the uptake coefficient of H2O2, which is you know, an example of a small polar molecule on titanium dioxide. This uptake coefficient, the probability of uptake actually goes down with relative humidity, and the same here is here. It's the interaction of isopropanol and alcohol with Gobi dust, and you can see that in terms of relative humidity, increasing relative humidity leads to a lower uptake probability. However, sometimes it goes in the inverse direction. This is the relative humidity. The red is a low and the blue is high relative humidity, and the volume fraction remaining of the heterogeneous oxidation of alpha pinene by OH actually is faster at high relative humidity. So at high relative humidity, this oxidation reaction is faster than at low relative humidity. So you can see that that the results actually are dependent on relative humidity and go both ways. I would like to draw your attention now in the last 5 minutes or so that I have. You can ask the question, well, what is the makeup, the composition of the surface on the examined mineral dust surface? Because we can use not only organics, but we use probe gases that actually sort out or interact specifically with definite surface functional groups. We have, for instance, taken bentonite, which is 95% weight montmorillonite clay, with hydroxylamine, with trifluoroacetic acid, HCl, NO2, D2O, I will come back to this, O2, trimethylamine, H2S, and so on. So these are the experiments that we have done. And let me take the example of D2O. We took D2O because bentonite actually has a propensity and pronounced propensity to absorb water. So in order to distinguish between the water that was already there and the water that we brought in, we use D2O. Then what we saw was exactly the same as the one for amorphous carbon. So that means that if we took the observed rate for adsorption in the to explain the desorption kinetics, we have this situation here. So this is the blue is the experimental rate of the experimental signal upon desorption, and the observed rate of adsorption in the uptake phase is 1.18. We had to increase the adsorption rate constant for the desorption phase when the sample was wet to 40 per second. So you can see that the enhancement factor is 34. We had to choose a rate constant that was 34 times larger for the desorption when the sample was saturated compared to when it was virgin, free of water, basically free of surface water, surface-bound water for bentonite. We see the same for Arizona test dust and water. Here we get the enhancement factor is 79, so which means that here we took we set the rate constant for adsorption equal to the observed one, which is 0.567. But in order to get a good fit of, we had to use a Ka for adsorption of water vapor on the water saturated ATD coarse sample of 45 per second, which is an enhancement factor of 80. So you can see that it opens up a new situation for small polar molecules like H2O, HCl, and NO2. These are the three exceptions that we noticed. The LAMU adsorption model is not fulfilled. We cannot use the LAMU adsorption model because the rate of adsorption of water, of small polar molecules like water, depends is autocatalytic, depends on molecules that are already adsorbed. And of course, if there is none adsorbed, the rate for adsorption, the rate constant for adsorption is much lower. Okay, so I would say that for bentonite, just in case you're interested, it's dominated by hydroxylamine. At 60% of a monolayer is adsorbed by hydroxylamine, and water is 10%, and acidity and basic groups are not that important. There is no significant O2 adsorption at ambient temperature. That was a question that's the reason why we took bentonite. Weak redox activity, few oxidizable sites, and the weak H2S but strong SO2 adsorber, but not nearly as much as hydroxylamine. So we think that hydroxylamine is a good monitor for surface hydroxyl groups. Hydroxylamine works with strongly acidic surface sites, but likely it's a specific indicator for the decoration of the surface with surface hydroxyl groups, in analogy to the titanium dioxide, which we analyzed about 10 years ago. Now, quickly, kaolinite, we did the same for kaolinite. I don't want to annoy you with tables, but here the conclusions are the same. The conclusions are the same. They're dominated by TFA, which means that the TFA is a strong acid. So they are actually a fairly basic, the TFA works or interacts specifically with basic groups and also hydroxylamine. So it's almost to the same tune, to the same extent. So it has weak redox activity, very little ozone and NO2 activity, but it's dominated by basic surface site and surface OH groups. That is for kaolinite, and for Arizona test dust. Here we have made runs with H2O that I have shown you before. Hydroxylamine is 40% again. It's likely acidic OH groups in analogy to results on TiO2. So on all of these surface clay minerals and on Arizona test dust, the conclusions are a little bit the same. And then in the end, I don't want to talk about that. These are very preliminary conclusions, but they are the same. Saharan dust are the same conclusions that we have reached for bentonite, kaolinite, and Arizona test dust. So in the end, I don't want to belabor this because that's just part of a table from a review article, and you can see that the hydroxylamine actually on 3 different titanium dioxide specimens actually are quite high as well. So that's why we think that for these mineral dust materials, that they are garnered with surface OH groups. Let's say that's we'll skip this slide and go to the conclusions. I have shown you, hopefully, that the desorption yields for semi-volatiles point to a stronger interaction of Arizona test dust in comparison to kaolinite. Same message when considering desorption rate or lifetimes for adsorption by measuring the rate constant for desorption and taking the inverse. The desorption kinetics of semi-volatile organics and ATD is consistent with simple reaction model based on Lamure adsorption. The rate is proportional to a number of free adsorption sites, and that is true for all the polyatomics that we have used. I don't want to sum them up here, but the exceptions are small polar molecules like H2O, HCl, and NO2, 3 molecules, or at least 2 of them that are atmospherically important. And if they interact with hydrophobic interfaces of amorphous carbon, they undergo autocatalytic adsorption and therefore strongly modify the chemical nature of interface. The same is true for the 2 cases, bentonite and kaolinite, kaolinite and ATD that we have used. So our results open up the specter that water adsorption, HCl and NO2 adsorption could be the same for amorphous carbon. We have proven this for 2 cases that we have examined in greater detail, namely by H2O and D2O adsorption, and therefore atmospheric dust actually would also be a good ice nucleus for at least in the stratosphere or upper troposphere, and would help in explaining contrail formation that is atmospherically relevant. They examined the mineral dust samples react with acids and bases, but in contrast are not redox active. But here H2O and D2O strongly modifies the interaction of bentonite and ATD cores. These are the two examples, but most likely also on other mineral dust materials. I think that's one of the principal outcomes of this research, that you have to consider atmospheric dust as a good ice nucleus in the atmosphere because of the special behavior. I would say that this autocatalytic behavior is a new twist. It's a challenge for modelers. However, I would like to point out that we have, in principle, gotten analogous results for interactions of water vapor on its own condensed phase, namely ice. Here we have also seen no saturation, but the adsorption of water vapor actually goes on unbeknownst or independent of any surface coverage. This actually concludes my presentation. I would like to point out to a failure. I hoped in principle at the outset to explain on a molecular basis why redox, why water molecules and other molecules are actually and organics to what extent do their adsorption behavior differ on kaolinite and on Arizona test dust. And as you have seen, the probe gas analysis of these mineral dust materials was not significantly different. So it does not explain the stronger adsorption behavior of these of the examined organics on Arizona test dust compared to kaolinite. So it is in principle a failure. I failed to show you in terms of a molecular view why the adsorption behavior of ATD of these organics on ATD and kaolinite is different. However, we discovered something else that was that may be of some increased importance, namely the adsorption behavior of small polar molecules on these mineral dust materials. I thank you very much for your attention. It took a little bit longer, but you can turn off anytime. Thank you for your attention, and I was prepared to take some questions, which I have during the presentation, my presentation at the Dust conference in Bari, but I have to tell you goodbye for now. Thank you, and take care of yourself.